Okay, before I start with new stuff, does anyone have any homework questions you'd like me to go over? Nope. Oh yeah, sure. On, do you have it with you? We have this object. Okay. This is rigid body statics number 2. Bless you. We have a rigid body like this, and the dimensions are 1 meter high, half a meter wide. And there is an unknown force in the middle. I'll call that R. I'm going to call it that because that's what it says to call it. Stupid. Okay. That was supposed to sound like Chris Farley. Oh, it says R, you stupid idiot. And then there's that T. And then the last force, oh no, there's a moment over here that's acting at this point, 60 Newton meters. And there's a 100 Newton force over here, and this makes an angle of 30 degrees. Okay, and we're going to assume that's in static equilibrium, and we're going to calculate that force vector R and that the magnitude of that force T. Okay, well, we're going to talk about, the next thing we're going to talk about is couples. So we're going to go through the, the steps of writing out a table for this and then do Newton's second law and the moment equation. But the one thing that's weird about this is there's this moment that just says 60 Newton meters. And it's like, what's the about point of that? Like it must change. Okay, well, it turns out that when you see things like that, that's called a couple. And it's just a moment that's totally independent of the about point. And I'll show you how that works right after this. But practically speaking, it's easier to use than other forces because you don't have to worry about the row vector, the force, any of that. It's just a moment. It doesn't produce any force. It's just you add the moment on. Okay, so what do we want to choose as an about point? We could choose anything we want. Might as well choose this, I guess, Like, why would I choose our about point there? It really doesn't matter. You can choose it anywhere, but it does simplify the math a little bit if you put your about point at the place where you have the most unknown forces. Okay, and the reason it simplifies it is then the row vector for those unknown forces are 0. And then when you take the cross product, it doesn't show up in the moment. So it simplifies things a little bit that way. But you can choose the about point anywhere, you'd get the exact same answer. In dynamics, that's not the case, remember, but in statics, that's true.
You have to put the about point there, because I did put it anywhere, and because I have too many variables, because if you put it at the unknown, then you have 0. But if you don't put it at the unknown, you don't have 0, and then you have too many variables.
Okay, let's do it at a different point and see how it works, okay?
Yeah, that's what I did, and I was like, oh, what the heck?
Yeah. Top left, over here where the moment is? Yeah. Okay, yeah, you don't have to do that. You might have thought like, God, I don't know what to do with that moment, so that seems like that's actually a really good thought. But it turns out it doesn't matter where you put it. So let me actually put it over, whoops. Let me put it over here. Okay, there's no loads acting there. And then, okay, row vector, force vector, moment vector. So for the force R, let me start with that. The row vector is, you have to go, so the thickness is 0.5, so you have to go in the positive x direction, 0.25. You have to go in the positive y direction, 0.5, to get from the about point to that p. Stop me if I do a step that you don't follow. The force vector is Rx, Ry. And so the moment is 0.25 Ry minus 0.5 Rx. And remember, that actually is a vector. That's just the z component of the vector. Okay, because we're in 2D. Next, I'll do the 100 Newton force. The row vector is 0.50. The force vector is 100 times cosine and sine of 30. So that's 86.6 and 50 for y. And so the cross product is positive 25. Then you have the force T. The row vector is 0.51. The force is the unit vector in the direction of the arrow times t. Well, that arrow is in the just positive x direction. So the unit vector is 1, 0. So t times 1, 0 is t, 0. And the cross product is negative t. And the last thing is that 60, that sort of odd thing that just is a moment that we're adding on. Well, we don't care about these things. And the moment, the direction of that moment indicator is, counterclockwise. That's the positive z direction if you use the right-hand rule. So this is just 60. Okay. So now we're going to add these up and set them equal to 0. That's Newton's second law. Add these up, set them equal to 0. That's the moment equation. Any questions yet? Okay, well, if we would have taken our about point where that force R is, we could have solved the moment equation for t right away and then plug that in. Now we're going to have to solve it as a system, but you get the same answers. So Newton's second law says Rx, Ry plus 86.650 plus t0 is equal to zeros. Well, we know that Ry then is equal to negative 50. The moment equation, so I'll call that rotational Newton's second law. That moment equation is actually derived from Newton's second law for rigid bodies. So 25 plus 60 minus t is equal to 0. 25 plus 60 minus t is equal to 0. No, I missed the r's. I wish it was that way. So 0.25 Ry minus 0.5 Rx is equal to 0. Okay, well, this tells us that T is equal to negative Rx minus 86.6. And so we have 85 minus T, so that's plus Rx plus 86.6 plus 0.25 Ry. We already know Ry is negative 50. Yep, minus 0.5 Rx is equal to 0. So we have, so negative 12.5, that's 72.5, plus 0.5 Rx is equal to 0, I think. So Rx is equal to 145. And then T is equal to minus 145 minus 86.6. Okay, so I think we get 145 minus 50. That's newtons. And then the tension is what's minus 145 minus 86.6? 140. 230.
I think RX is supposed to be negative.
Rx is supposed to be negative. Yes, that's right. And so 145. So what's 145 minus 86.6? 58.4. Is that what the solutions say? Wouldn't that be awesome?
Solution says 231.6.
Well, this is how you do
Yeah,
it.
negative 145 minus 86.6. You get negative 1.6.
Oh, so somewhere I made a mistake. Stupid mistakes, but anyways, this is how you do it, and if you do it right, you get the same answer no matter what you choose as the about point.
Cool.
Any questions about that? Okay. So thank you. Okay, so what's up with that pure couple that we just added on? Is that like a physical thing? Okay. What's up with that additive moment of 60 Newton meters? Let's say, can that represent something physical, something real, you know? Yes, it represents something called a couple. And that's what I'm going to talk about now. Okay, so couples. So to understand, okay, well, remember that couples are really the moment of a couple. People call them couples. And a couple is a pair of equal and opposite forces acting at a distance from each other. Let's say acting at a distance. Okay, so if you have a body like this, and you apply a force F that way, and somewhere else you apply a force F in the exact opposite direction, that's a couple. And the interesting thing about couples, the unique thing about couples, is first, notice that it doesn't produce a net force because it's two equal and opposite forces. And second, the moment it produces is the same no matter what about point you choose. Okay, that's pretty surprising because, so first, let's think about or compare to just the moment of a regular force. Okay, so let's say there's the object. Here's the about point. Here's the point P. And this vector, I'm just drawing that vector in there to represent F. Okay. So the row vector is this. And how would you calculate that row vector? Well, that row vector you can get by just subtracting the position vector P minus the position vector A. Okay? So the moment produced by F around that about point A is rho crossed with F. I guess let me write that step in there. That's the definition of a moment. And you can calculate that as P minus A crossed with F. Okay? And then you can distribute through that cross product, and you get that the moment is equal to the coordinates of where the force is applied, crossed with F, minus the coordinates of the about point crossed with F. Okay? So there's no denying, there's nothing canceling this. The moment of a force depends on that P. There's nothing you can do about it. Wait, God, I feel so rusty this semester. It's so weird. I wonder if it's from doing a lot of online stuff, I think. That is not what we wanted. We wanted to show that it depends on the about point. But it's the same thinking, So the moment of a force depends on that about point. And we already knew that if you choose a different about point, you're going to get a different moment for all your forces. Like, you know, if you choose your about point to be where a single force acts, then that force produces 0 moment. But now let's think about a couple. Okay, so you have this arbitrary body, and now you have 2 locations. Let's call this one P1, and that's where we're going to apply this force F. And it doesn't matter which one you call F and which one you call negative F. It's just 2 forces in opposite directions with the same magnitude. So, but I'll call the one F that's going to P1, and I'll call the one negative F that's going to P2. Okay. And then let's choose an about point. Doesn't matter where. So for this force F, this is the row vector. Call that row 1. And for the force negative F, this is the row vector. Call it row 2. Okay, and the total moment is just going to be the sum of the moments of those 2 forces. Okay. Well, what do you expect to happen? I'm telling you that the moment of a force depends on the about point, but a couple is not going to depend on the about point. So what do you expect to happen when I go through these equations and simplify it? It's the A's are going to cancel out, and they're just not going to be in there. Okay, so where you can see for the moment of a force that A is in there and there's nothing you can do about it, this one, it's gone, and it just doesn't matter. No matter what about point you choose, the moment is going to be the same. Okay, so let's see that happen. Okay, so the total moment.
That because the forces are in opposite direction.
Well, it is going to depend on that. You'll see where it cancels in the equation. But so let's say the total moment about A is equal to row 1 crossed with F plus row 2 crossed with F. Row 2 crossed with negative F. Okay, and then substitute in, row 1 is the coordinates of P minus the coordinates of A. And row 2 is the coordinates of 2 minus the coordinates of A. So substitute those in. You get P1 minus A quantity crossed with F plus the quantity P2 minus A crossed with negative F. And now go through a little vector algebra. So you get P1 cross F minus A cross F plus P2 crossed with negative F minus A crossed with negative F. Well, you can pull those negative signs through, and so this is P1 crossed with F minus A crossed with F minus P2 crossed with F plus A crossed with F and that's the step where those 2 cancel. So A is gone, and you're left with this sort of simple thing that says, notice for the moment now I'm taking out the dependence of A as the subscript because it just doesn't matter. M is equal to, if I regroup these now, P1 minus P2 crossed with F. So the moment of a couple is the same no matter what the about point is. Okay, so in the table that I've been filling out for these, if you have a couple of negative 40 Newton meters, let's say, okay, so I could write this as a moment in the counterclockwise direction shown with a negative, okay? Or I could write that as a clockwise direction with a positive. It's the same thing. But you would put this in the table this way. Forget about these. They don't, a couple of forces don't add up to a force. So that's just going to be 0. You don't care about the about point because it's a couple, and you just put this in as negative 40. And notice that's what we did in this example problem. Where was it? Okay, so for each one of the forces, I calculated the moment, and then for that 60, which now we know represents a couple, I just added in the 60 and ignored those two things. Okay? When do couples come up? Well, so what we're going to talk about next is joints. And anytime a joint keeps a body from rotating, it's applying a couple. So it happens when a joint prevents a rigid body from rotating. Okay, so like imagine this cantilever beam that's rigidly attached, welded or glued or whatever to the wall. Okay. If you think about what the wall is applying to that body to keep it from, so let's say there's a force like this. Okay, so that force going down is trying to rotate that rigid body clockwise, right? So how does the wall prevent that from rotating clockwise? It has to provide a counterclockwise couple, okay? And that counterclockwise couple is like this. It applies a force there and a force there. Okay, well, really it applies infinitely many forces above the center line going to the left and infinitely many forces below the center line going to the right. But you can think of it as like this sum of, this infinite series of couples. And the effect is those provide a moment, but no force. Okay. Okay, so now we're getting into joints, and that is, to me, maybe the single most important topic to feel really fluent in this whole class. So joints, and we're going to do it first in 2D, and then later we're going to do it in 3D. Not too much later, pretty soon. So a joint is a connection between bodies. And what it does is it determines what relative motions between bodies are disallowed. Okay, so it's important not to think of a joint for understanding what a joint does mathematically. It's important to think about what motions are restricted, disallowed, rather than what motions are allowed. Okay.
It's like you try to like move your arm in some direction, your joint's like, oh, well.
Well, yeah. I mean, if you try to shoot your arm across the room, your your ligaments are like, like you got to keep that here. We need that later for lunch. So.
Can eat your arm?
But like a knee is a good example. Okay, well, I brought these visual aids. Okay, so here's basically your knee. You're gonna want to go easy on it. So let's say that this part is fixed. What relative motions are allowed by the top part? We're doing 2 dimensions. So for now, we're not going to think about out of plane stuff. So just think of it as this is free to move. We're considering the motion that happens in this one plane that you can see. Okay. Well, how many degrees of freedom would this body have if it wasn't connected to the joint? How could it move? It could move along one axis. Okay. You can choose whatever axis. It could move. So let's think of the whole thing as a rigid body to start with. Okay, it could move along one axis that we choose. It can move perpendicular to that axis. So that's 2 degrees of freedom. And it can rotate in the plane. Okay, so it has 3 degrees of freedom. So that's sort of the starting point. Now we're fixing the lower leg, and thinking about what degrees of freedom does this thing have now? Okay, choose any axis you want. Can this thing at this point of the joint move along that axis? And the answer is no. Okay, don't think about the rotation, just think about the position of that connecting point. Okay, I can't move it this way, and there's no axis where I can. Once I've chosen that axis, I also can't move it perpendicularly to that, but I can rotate it. Okay, and so this joint, your knee, has restricted all translation, but it hasn't restricted rotation. Question?
So if it's free to move, then you get dynamics where your about point has to be that point in the center that's rotating around. If your about point, since it's not moving, can still be anywhere.
Yeah, that's right. I mean, everything we're going to do is in statics, so all of this stuff is just kind of a way to think about it. We're going to think joint by joint, and then come up with a whole system. In dynamics, by the way, if this body has this one point that's fixed in space, your about point could be the center of mass, or it could be that point that's fixed in space. But since in the end, this is going to have other things that keep it in static equilibrium, we could choose the about point here, or here, or here, or whatever, and get the same answer. So before a rigid body is connected to a joint, it has 3 degrees of freedom. That's because we're in 2D. And those are translation along an axis, translation perpendicular to that axis, and rotation. Rotation. What joints do is they apply forces and couples to things to disallow those degrees of freedom. So joints apply force components along axes to disallow translation along those axes. And they apply couples to disallow rotation. Okay, so now I'm going to go through all the various joints that you'll see in two-dimensional problems. So here's a list of 2D joints and the loads they apply. Okay, well, there's only 3 degrees of freedom that are available to be taken away in 2 dimensions, right? I mean, that's all something has. If it's in outer space, it has 3 degrees of freedom. And so we're going to deal with joints that limit 1 of those degrees of freedom, joints that limit 2 of those degrees of freedom, and a joint that limits all degrees of freedom, and it's just rigidly fixed. And that's all you can do in 2D. You can only take away those 3. Okay, so I'm going to put them into categories based on how many loads they apply. So I'll call this joint category 1. These are joints that apply a force in a single direction. And because all they apply is a force in a single direction, they introduce 1 variable into Newton's laws. Okay, well, there are a few of these. One is a contact without friction, and we've already seen that in our particle statics. So if you have a body that's in frictionless contact with the ground in this case. Let's say this is body 1 and this is body 2. Then a free body diagram of body 1. I'm just ignoring all the stuff that's happening up above. But you would have a force that's perpendicular to that surface. And a free body diagram of body 2 would be equal and opposite. Notice that in this case, could that R go the opposite direction in a frictionless contact? You know what I mean? So on a lot of these joints, we'll set up the free body diagrams like this. What if I got a negative answer for R? Is that physically possible? No, not in a frictionless contact, because that would be saying that this body 2 is pulling down on that. You know, that can't happen. So notice that for a contact without friction, R has to be positive. Okay, the second type of joint in this joint category 1 is a roller. You can draw that, or you'll see that drawn as just like a ball separating the two bodies, like sort of a ball bearing, or you'll also see it as like a roller skate. But you treat both of these two things the same way.
Little pair of finger skates.
Yeah, yeah. Okay, so this, we'll call this body 1 and this body 2 in both of these cases. So a free body diagram of body 1. That force is going to be perpendicular to the surface. And for body 2, it's going to be equal and opposite. What about this one? Could that R be negative on a roller? No, because if you got a negative answer for that, again, that would be like the ground pulling down on the wheel on the roller. That doesn't happen. So again, R has to be positive. And then the last type of joint in joint category 1 is called a pin and slot joint. So there's our body 1.
Ooh, this is like wooden dowel.
Like what?
I like a wooden dowel.
A wooden dowel.
Like if you were doing like making like a puppet or something.
Mhm.
Look like joint.
Yeah, right. I can show you exactly one of these. I have it sitting right here, you know. It's sort of small, so it's hard to see. But if you think of the one I'm holding here as body 2, and this one up here as body 1, you can see this thing is free to slide along this one chosen axis. But if you try to pop it out of there perpendicular to it, it can't move perpendicular, and it's free to rotate, okay? So there's one single force that resists translation perpendicular to the slot. Everything else is free to happen. Okay, so a pin and slot joint if this is body 1 and this is body 2, so I'm just drawing that slot in so you can see that this force is perpendicular to that slot. Call that R. Then the free body diagram of body 2. The force is equal and opposite. And in this case, could that R be negative? Yes. In this case, notice that slot can push or pull, to resist perpendicular motion of that top body. Okay, so notice whether you choose R this way or the opposite direction is arbitrary, and so you can get positive or negative values. Okay, joint category 2. There's only 2 joints in this category. So these joints apply a full force vector disallowing all translation but no couple. And because of that, they introduce 2 variables into Newton's laws. There are 2 types. The first one is a pin joint, like the knee joint thing that I showed you here. So the object can rotate around a pin. Also, you might see this called a hinge. So if this is body 1 and this is body 2, I'm sorry, I don't mean to race, but I am trying to finish this before class ends. Then a free body diagram of body 1 looks like an unknown force vector. And I'm going to write that as the force on 1 by 2. And free body diagram of body 2. Well, that would be the force on 2 by 1. And Newton's third law says that's negative F12. The other joint that applies a full force vector we've already seen with particles. That's a friction contact. So a friction contact, if there's body 1 and there's body 2, it works the same way. So for body 1, you'd have this force F on 1 by 2. And for body 2, you'd have a force negative F12 again. Okay, this is the last thing I'm going to say. I just want to have all this together in your notes. So now the last category is joint category 3. That's just one that disallows all motion. By applying a force vector and a couple. And that introduces 3 variables into Newton's laws. There's only one of these. It's called a fixed or a weld joint. You'll see it drawn 2 ways. Just like that, like it's glued, or you'll see it with a like a sort of a dovetail joint, a little slot. Call that body 1 and that body 2. Okay, last 2 things, and then you're free to go. Free body diagram of body 1. Looks like this. There's a force vector, force on 1 by 2, and a couple that I'll call couple on 1 by 2. So there's the 3 variables and the free body diagram of body 2. There's the force negative F12, and the couple is also equal and opposite. And so I'll write that as negative couple 1, 2. The couple has to be equal and opposite because remember what a couple is 2 equal and opposite forces. So, and those just switch because of Newton's 3rd law. So that makes the couple opposite. Okay, that's all. Any quick questions?